Alright, so in this video we're going to do something pretty interesting. We're going to look at what happens to the gravitational force when you are inside of an object. Okay, and so one of the things that means we need to focus on is the density of the object that we're in becomes very important. Because as you go, like say the Earth, if you go inside the Earth, you've got some mass that's below you, and then some of the mass of the Earth is above you. And so we have to understand kind of how the mass is distributed to understand how gravity will play a role. All right, so let's say that we've got a planetoid here. So, I'll use this to kind of show like areas of density that are different. Okay, and I know this is very exaggerated in terms of density, but you'll get the idea. So it's definitely a non-uniform spheroid. Okay, and so what we want to do then is, if we imagine that we drilled a hole straight through the center of this. Okay, so I'll just take away a tiny little part. Okay, and then we will put a mass somewhere inside of that hole. So the idea is, if I take a mass, and let's say I put it some distance r from the center of the planet, okay, what's important to understand is that that distance r forms a sort of like a shell, okay, where it's inside of the planet, which has a radius of, say, capital R. And it's important to understand that when you're inside that shell, there is no gravitational force caused by the outside of the shell. Okay, let me rephrase that. The gravitational force from the mass that's outside the shell matters, but since you're being pulled in all directions at once, effectively all the forces cancel off. So there's no net gravitational force when you're inside of that shell. So the only thing that's causing a gravitational force is the mass that's inside that shell you create. Okay, so if we wrote for this planet, so I wrote a density function. Let's say this is how the density of the planet varies. So the mass divided by pi times the radius of the planet to the fourth power times r. In other words, the further away you get from the center, the more density it has. Now, when we write our gravity equation, so gravity is the gravitational constant, product of the masses divided by the distance squared. Okay, the MP term, which is the mass of the planet, is referencing only the mass of the planet that is inside the sphere that we would draw based on our location. Okay, so if I put the mass at a distance r from the center, and then imagine drawing this is a 2D image, so you'll see me draw this circle, but imagine that the circle is, part of a 3D sphere. Any mass on the outside of that sphere does not contribute to a net gravitational force. Okay, and one of the things you can refer to this as is a Newtonian sphere. Okay, or shell is another way to think about it. Okay, so in order to calculate the mass that's on the inside of the sphere, we have to go back to like what we did before when we were doing center of mass and rotational inertias. But we're talking about a sphere, so we're doing three-dimensional density. So density is mass per volume. So the little bit of mass dm is equal to the density times the little change in volume. And so if we write out the equation for the little change in volume, that would be, well, the surface area of the shell, which would be 4 pi r squared, times the thickness of the shell, which is dr. Okay, so our density function was given m over pi r to the fourth times r, and our small amount of volume. So we can do some quick algebraic cancellations here. We'll see that the pi's go away, and then we'll be left with 4m over r to the fourth, and then r times r squared would give us r to the third. Okay, so for this problem, this is a representation of how much small amount of mass there is at every piece of radius. So if we want to figure out the mass inside, the limit of our integral will only go from the center of the planet, 0, out to the place r where we put the mass. That would be the outer edge of that inner shell. So we put in our function for dm, That's 4m over r to the fourth times r cubed dr. And then we simply just need to solve this for finding out the mass on the inside. So 4m over r to the fourth is a constant. The integral goes from 0 to r. And then it's just r to the third power dr. So let's take an antiderivative of r cubed. Okay, that'll just become 1/4 r to the fourth power. And then when you plug in the limits, 0 to r, 0 goes away, and we just get r to the fourth power over 4. And you'll see that the 4's cancel. So you get the mass of the entire planet times the little r, where our mass is, to the fourth power, over the radius of the planet to the fourth. Now, when we go to plug into our gravity equation, that means we have this expression to put in for the mass that was inside of our shell, okay, times the mass of our object. Okay, and then we can do some simplification here. So the r squared in the bottom, we'll get rid of 2r little r's on the top of our inside mass expression. So we'll get a final force of gravity of gravitational constant times the mass of the planet times the mass of the probe times the radius where we are, where we put the mass squared, divided by the radius of the whole planet to the fourth power. Okay, so calculating the force is the same way that we've been doing it in terms of gravity, but when you're inside of the planet, it's important to remember that only the mass that's inside from where we are accounts for finding the gravitational force. Now in this problem, the density was not uniform, and so we had to come up with an expression for dm. But if it was a uniform planet, well, then you wouldn't have to do the dm's. You could just say that the density is the whole mass divided by the whole volume, and then we could have done the work with that, and it probably would have ended up being a little bit easier. Okay, but it's important to just understand that concept that when you are inside the planet, only the mass that's inside of that sphere that you draw accounts for creating a net gravitational force. All the mass on the outside of that shell, the gravitational forces caused by it are in all directions, and therefore will add up to 0 and create no net gravitational force because of those outside masses.